The speaker of the afternoon is Kostas Skenderis, who used to be in Amsterdam.
Okay. Thank you very much. Thank you very much for the invitation.
Oh yeah, right? For those people who were not here this morning, at 5 p.m. there will be wine served upstairs. And tomorrow morning there will be sort of a second focus, more like discussion session. Informal about not entirely sure. I haven't quite asked Joe, but Antonio said that Joe was asked.
Okay, thank you very much for the invitation to give the talk in this nice workshop. It's the second time I come back for this. So this is going to be a Blackboard talk. If I don't write big enough, just shout, or you can also come closer. And I'm trying to use all the Blackboards. So the title is AdS Ricci-flat correspondence. And this is work I have been doing together with Marco Caldarelli, who is a postdoc in Southampton, Johan Kantz, who is sitting over there, and Blaise Boutereau, who is a postdoc in Erdita. So we already had one paper about this topic, and we're about to finish a second one, and we also hope to have more work, maybe in this year, maybe not. So what I would like to convince you today that this is really a program, is not just one work off, one piece of work. And there's a lot of things to be done, and I think there's a lot of space for contribution for many people. So I would also like to invite the audience, if you find it interesting, to join us in this work. So what I will do today is I'll try to give you a flavor of what we are doing, and I will start with some general introduction, and actually this is going to be mostly a lightning review of holography, because in a sense where this is going is we'd like to understand holography for Ricci-flat spacetimes from holography in AdS, something which is very well understood. And so in order to kind of tell you where we're going, I also have to remind you some of let's say standard material that perhaps some of the younger people have forgotten. And then after this introduction, I'm going to introduce the correspondence. And then we're going to discuss examples, and depending how much time I have, I'm going to discuss more or less, a few or more examples, and then I'll finish with an outlook. Okay. Okay, so holography is now about more than 15 years old, and we learned a lot of things during that period, but we still do not understand, let's say, the underpinning mechanisms that make holography work. The general arguments from Toft and Susskind from 20 years ago indicate that holography is a general phenomenon. It's true for all theories of gravity, but in detail we really understand AdS, and all other cases we understood, that some of them I'm going to review today, are linked to AdS in one way or another. So if holography at the quantitative level is really true aspect of quantum gravity, we should be able to have a formalism that works in all cases. So that work is a step towards that direction. So let me start from, let's say, essentially 1997, where AdS-CFT was first introduced. So in that case, we understood holography by looking at near horizon limits. So this gave, say, AdS-CFT. And the case which was first understood was the so-called say conformal branes, namely the D3, M2, M5, or certain intersections. And in this case, it was understood that the dual theory has something to do with AdS. Now we understand this a little bit better. So in all of these cases, there is a universal sector. And this universal sector describes correlation functions of the stress-sensitive tensor. So all CFTs have a stress-sensitive tensor which generates the conformal group. And AdS is in a sense a very clever way to package this information when the CFT is a strong coupling. So then we have the description using AdS gravity. And AdS gravity, of course, has, let's say, the basic solution is AdS itself. And this solution just corresponds to, represents the vacuum of the dual theory. But on top of the vacuum, we can consider excitations. So the general problem is that we want to turn on excitations. And here, R equals 0 is the conformal boundary. And when we choose AdS, then we pick as a boundary metric the flat metric. In order to generate more interesting cases, we need to change that. So have general boundary conditions are specified by a general boundary metric, which in general can depend on the boundary directions. And then this basic solution is now generalized to that one. And then once we know this, then you can now set up in complete generality to compute the correlation functions of the stress energy tensor by computing the expectation value of the stress energy tensor in the presence of sources, and that is more or less indicates that this is in the presence of sources. And to do that, you need to functionally differentiate the renormalized action with all counter terms added, etc., with respect to this boundary metric. And this can be done in complete generality and gives this answer. Now, if you want to study the excitations around this, then you say your boundary metric is Fij plus a small fluctuation. And then you want to know what is the relation of this guy with that guy, or more generally, the relation between this and that. So then from here, you find that this is whatever background value of of that coefficient there is. And then essentially you have an expansion in this boundary quantities. So what these guys are, these are really the quantum field theory data. So this is a 2-point function. And in order to compute a 2-point function, you need to know the response of the theory to linear order in H. So you need to solve linearized equations. And this is 3-point function. Then you need the second order perturbation, etc. So that coefficient here, if you compute it with this boundary metric, encodes all correlation functions of the theory. So it really encodes all information that the boundary theory has. So just to prepare for what is going to come in a few blackboards. So suppose we want to look at the transverse traceless mode of the graviton, which is actually the only thing which is there if we just have gravity. Then one can show that the linearized perturbations is just some constant tensor times field phi, which is basically massless. Now, once you have this and you solve the field equation, with regularity in the interior, so then you find that this phi and this guy here is just a 2-point function. So that's where the 2-point function sits. Okay, and you can do that for higher point functions. Okay, so that's a story which was understood 20 years, 98, 99, or maybe a couple of years later. Okay, so in general, I would like to generalize that story in general to any theory. We like to understand what is the dual theory and what are the field theory data set. So this story we knew there was a duality because we had this very nice near horizon limits which gave an existence proof of a duality. So around the same time when this happens, people also study not just these branes but also the non-conformal branes. So essentially D0, D1, D2, D4. And the same argument that gave rise to AdS-CFT here works pretty much in a similar way over there. So there is a holographic duality in this story as well. And but these theories are not conformal anymore. So, and the dual theory, so the dual theory is not conformal anymore. So the universal sector does not involve just the stress energy tensor. Now it involves the stress energy tensor and another operator. And this other operator is essentially the Lagrangian of the theory. And this universal sector, like here, that we had a description in terms of some Lagrangian, that also there is this universal sector has also a description in terms of a d-dimensional, d plus 1 dimensional Lagrangian. Which is now slightly more complicated. So this Lagrangian encodes this universal sector, where this parameter sigma just depends on which of the theories we're considering. So in all cases, there is the same effective action with different value of sigma, where the sigma values are these numbers for this case of the branes. So again, on general grounds, one expects to be able to set up holography for that theory. But of course, the field equations of that theory are a lot more complicated than the field equations of that one. Nevertheless, since there is an existence proof for the duality, one should be able to set it up in a way which is analogous to the setup we just had for the AdS braids. And indeed, that turns out to be the case. So by brute force analysis, one can set up holography in a similar way. And what I mean by brute force analysis is that over here one had to understand the asymptotic structure of the field equations, what I wrote up here, and one had to be able to do this differentiation, finding normalized action, and all of that. And with a lot of work, we did this in 2008. There were 2 papers and
here, this is in the conformal form. This one.
this here we use, so this is called a dual frame.
Dual frame.
Yes. And it's very useful when you do the you set up holography to work on that. But then after the hard work, so let's say the math worked, but I was still unclear why we're able to do that computation. Then we understood why it worked so well. It worked so well because this specific action can be obtained by AdS by the following fashion. So you start from AdS gravity, and you put that on 2 sigma minus 2 torus, and then reduce. So this is a consistent truncation. There is a consistent truncation. And this theory here just gives this non-conformal brane. So the reason we're able to do that computation was because you can start from gravity in 2 sigma plus 1 dimensions, then reduce over the torus. And once you reduce over the torus, the dimension of the torus just becomes a parameter in this effective action. And then one can analytically, one can continue the value of sigma from integer to some general value. And you can do that as long as you don't hit any singularity in this effective action. So in all of these cases, this does not happen.
I mean, you have to careful, right? So it does happen if you would be
Yes.
truncating a vacuum state of your high dimensional AdS because torus shrinks to zero size.
So it can happen that, I mean, you can see from here, let's say, you expect to have a trouble if 2 sigma is equal to
No,
D,
but
for
I'm saying
instance.
something even simpler, right? I'm saying that if you are doing this truncation and your AdS, you happen to look in the vacuum, right? So in AdS, what you would call a torus, right? So those would be normally some, say, Poincare interactions, but now they would be tori. And so that torus would go to zero size in the infrared. And so you might worry whether your truncation is consistent, or maybe there are other degrees of freedom.
Yes. So with consistent truncation here, I mean,
The closed string sector.
something technical. So I mean that all solutions of this theory,
In a closed string sector, it would be, but
yeah. So within,
about trapped grains or, addition. If I were to go beyond the gravity approximation.
so if you were to go beyond the gravity approximation, or if you start adding more fields, one has to re-examine whether, let's say, this strategy of understanding holography that would work beyond the sector we worked on.
However, you know for sure that as long as, for example, this is definitely true if there is an infrared cutoff or gap in the states that you study. For example, for the hydrodynamics, you would do any finite temperature, then this all goes.
No, so showing the hydrodynamics works exactly fine.
I showed that as well. Some papers.
Yeah. So this map between AdS in 2 sigma plus 1 and this non-conformal in D plus 1 via a reduction on T sigma minus D controls both the UV properties of the theory and also the infrared properties of the theory, at least for the subsectors that we're discussing here. So then all the formulas you need for the non-conformal branes essentially descend from the formulas I review up there, simply by following this map. And all of these formulas we sweat for a year to produce, you can now get them in one afternoon by doing this reduction. So that controls both the, as I said, both the UV properties, so all the renormalization properties of that theory, I just given by the renormalization of the AdS parent theory. Then the correlators that we get, they have a hidden conformal structure, and that comes because the AdS correlators, of course, they were conformal, and also properties in the infrared, like the hydrodynamic expansion, is also controlled by the same conformal structure. So the punchline of this is that holography follows from that of AdS. And then there is an underlying hidden conformal structure. For example, in hydrodynamics, the bulk viscosity essentially follows from the shear viscosity because there's this generalized conformal structure. Okay, so in a sense, so this is a case where the asymptotics is not AdS. It had to be holography, and there is holography, there is a framework which is completely satisfactory. But this is the case also that this non-AdS, I would say, holography, in a sense, is linked to the AdS via that procedure, which we call generalized dimensional reduction. Well, it's clearly dimensional reduction. It's generalized because after we reduce the theory, we continue sigma from its integer value to be a general value such that this effective action is still well defined.
Just for this specific way of looking at non-conformal holography, there are other examples of non-conformal holographies which would not get, for example, there is a hydra and lots of other stuff, not necessarily examples of non-conformal, other examples of non-conformal holography can be understood as a reduction of some conformal model.
At the same time, there is no other set of theories where holography is set up at this level of
Oh yes,
of rigor.
mass deformations. Like mass deformations or, or the flux geometries on a conical.
But I mean, none of this have, let's say, a well-defined view theory.
No, it is at the exactly the, I disagree with you. It is exactly the same level. I can compute you all the correlation functions. You have to prove that you can remove divergences and all that stuff, and it has been done. Why are you saying it hasn't been done?
Well, we can discuss in private.
So you're saying that, no, we can discuss in private, but I wanna hear your public statement. So you're saying that, that we don't understand how to holographically, say, renormalize n equal to star model? Just doing math.
So there's no, let's say, formulas which should derive the sum level of rigor as the AdS was.
Well, okay, so that's...
So in a sense, this was a success story, and now we'll try to see how much of this success story we can repeat in a more general context. So, actually, maybe I'll do it in a minute once. Okay, so that's finished, in a sense, my introduction. So here I'm going to define the AdS Ricci-flat correspondence. So this is going to be a correspondence between solutions of two different theories. One is AdS gravity, like we had earlier, and the other is just standard Ricci-flat solutions. So So now the claim is that there is a correspondence between the following class of solutions. So we look for solutions with negative cosmological constant, which are of the following type. Or this wise Torus. So these solutions are specified by a P plus 2 metric and a scalar field. And the other solutions are just Ricci-flat solutions. And this is an n+1 sphere. So this solution is also specified by a scalar field and a p+2 metric. And the claim is that for any solution of this type, there is a corresponding asymptotically flat solution of that one, of the type over here. Well, the relation is the following. First of all, here I indicated that this p+2 solution could depend on the space-time dimensions, and same thing for the scalar field, and same thing for the scalar field here and the metric. And the relations are the following. So suppose I give you a solution of this form. Then the corresponding metric over here is going to be the same function of x and r, but the parameter n, which is related to the dimension of the sphere, is going to be equal to minus d. And exactly the same thing for the scalar.
I said this is a gravity, classical gravity.
Classical gravity, yes. Okay. So this is the correspondence between the different solutions of the different theories. So there is one correspondence. One has, let's say, torus, and the other has a sphere.
What is that minus sign there? N equals minus d is a bit funny.
N equals, yes. So you find this as a function of d, and then you substitute for d minus n, and you get the other one. And we will see an example. But let me first indicate how you prove this. And then you will see how it works. So the way to prove this is to do this generalized dimensional reduction I discussed over here. So on this side is actually exactly that story. So we reduce this theory on Td minus p minus 1. And when you reduce this, there is a consistent truncation in the formal sense, namely if I substitute this metric here in the field equations, and then I work out what conditions the p+2 metric and the scalar field satisfy, and then the equations that you get are obtained by the following action. Okay, so again, starting from that, you can reduce over the torus, and then the field equations that follow from that action are exactly what one gets if you plug in that ansatz into the equation on the top. And you can do the same starting from here, where we now reduce over the sphere, and we end up exactly with the same action, except that now n is equal to minus d. And you get the same action here, where instead of d you have minus n. Now if you put here instead of d minus n, you can see this is still a positive coefficient. So this is still an allowed generalized dimensional reduction. Yes?
Do you have to solve the AdS equations of motion for arbitrary dimension in order to find the corresponding?
Yes.
Yes.
So this clearly works for analytic solutions, right? To the equations of motion. But if you have non-analytic solutions, then would these still carry through?
Well, first of all, that step.
Yeah, that step is okay.
That's okay. And then what I'm saying is this effective action is the coefficient d appears in this effective action as a parameter, and then as long as this effective action is not sick as we change that parameter, the general features of the solution to the field equations will remain the same. That's the statement. Good.
I'm probably struggling with a notational issue, but if d was positive, so n becomes
Yes.
negative, and Sn plus 1, what is a sphere?
So let me give,
Minus-
so next I'm going to give an example. We're going to see explicitly how it works. So you do it for general d, so the coefficients are now functions of d.
I'm not asking how it works yet, I just want to know what is S minus 5.
In both cases, n is always positive and d is always positive. So you're never considering spaces in negative dimensions. It's the link of the two as a functions of the space-time dimension that that requires that change of sign. And I think it will be clearer when you see it in the example, which is what I'm going to do next. Yes. I mean, at this level, we're just making a statement about solutions of two different theories, and we say that the class of solutions of the one are in correspondence with the class of solutions of another. Just a classical statement. So the simplest example to consider is just to just look at exactly AdS on p minus 1. So now let me just work out this case in detail. So here I just compactify some of the boundary dimensions on the torus. So this metric over here is of the form I indicate up there, where ds p plus 2 hat is basically this part. And the scalar field is the coefficient of the torus. Which is just L squared over R squared. So now from here I can just solve for phi hat. Okay, so this are my data. So this metric, this specific metric does not depend on D. So there's no self-validity, but this one you can see this depends on D. So now I'm instructed to, my phi tildes are obtained from the phi hats by just taking D to be minus n. So that gives n plus p plus 1. And this is the same thing as the sigma hat, the tilde, because I just know D there. And now I can put them together. Okay, so to do that, I have to multiply, I have to put first the scalar field. So the scalar field from here to that power, you can see this factor here is what's in the denominator over there. So this is an R square over L square. And then inside, I should put the p plus 2 metric. And then I should put L square d omega n plus 1. Okay? So now when I multiply this with that, these factors cancel out. And the L's cancel, and I get the R square there. And now this, together with that, is just n plus 2 plane and radial coordinates. So all of this is just Minkowski n plus p plus 3. So here you see, so this n is still positive. It's more that when I wrote phi as a function of the coordinates, to get it from here to there, I took d and I substitute minus n. But d and n are never in the same equation. So you either have d or you have n. Okay, so since one of the basic solutions on the AdS side is again mapped really to one of the basic solutions, the basic solution on the Ricci-flat side, it's just Minkowski space. So here R equals 0 with a conformal boundary. And the data that we fixed, it was really the metric, this metric eta AB. So on this side, R equals 0 is now the center of the space. So essentially, the metric that we fix over there is that we pick p-brane boundary conditions. So this corresponds to p-brane on Minkowski and plus p plus 3. So we already see that starts looking different than in AdS. Of course, over the last 10-15 years, I mean, many people, including myself and people in the audience, try to set up holography in asymptotically flat spacetimes, but we always look at data at infinity, and that doesn't really work. Here we see that now that we connect this asymptotically flat spacetimes to something where we understand how holography works, the holographic data do seem to sit in a different place, not an intuitive place where one might expect them to be.
If I want to get a Ricci-flat solution, which is asymptotically flat or asymptotically Kaluza-Klein, this means I have to choose a solution which has a Poincare horizon in the AdS case?
So for all of these cases we understand with this map, it has to have, it has to be some Poincare horizon.
So if I destroyed that with some different IR behavior, or if I had even an AdS black hole.
AdS black hole, if I have AdS black brane, I can do.
And and you get an asymptotically flat solution?
Yes. Then I will discuss this.
But not for global black hole in global AdS.
So global AdS is not automatically of that form. So one has to, in a sense, tweak the construction, which we haven't tweaked it yet enough.
Minkowski from the AdS perspective, where does that go to?
So the conformal infinity of, so the R to infinity kind of limit of that seems to be in the center of AdS, whereas the killing horizon of AdS sits. But there's still a lot of things to understood. So we mostly, so far, the name of the game was to start on the AdS side, where you kind of understand the structures and see what do they become these structures when you move to the Minkowski side. Is it a canonical map? Is it something you already recognize? Can you see where the holographic data, we already know where the holographic data are on AdS. So we'd like to see where that data are mapped in Minkowski, because that is going to give us a better intuition where the holographic data of Minkowski should sit.
This is very different from this other work where people take the large radius.
Yes, it's very different. It's very different. I would say almost completely different. I mean, here, in a sense, we mapped, we saw that, as I discussed earlier, just empty AdS was the vacuum solution on the CFT, and that mapped to, in a sense, the vacuum of the vacuum on the Ricci-flat side. So now let's try to do, let's say, the next more complicated case. Let's try to see what happens in this two-point function commutation I described earlier. So let's put a linearized fluctuation on AdS. And this linear effect corresponding to two-point function. The way I described earlier. So this means that we're looking for perturbations, linearized perturbations, which they have some, let's say, transverse traces polarization tensor. Times massless scalar. And now to compute the two-point function, we need an exact solution of that, which is regular in the interior. So then the regular solution, of course, in this case, is completely unknown. This is given by this Bessel function of that order. And once we have the regular solution, we can expand it asymptotically in order to recover the data. So this piece over here is really the correlator of the dual theory. So essentially, from here, we see that the two-point function of the stress-energy tensor, it has some projector to the transverse spaceless piece times k to the d. And that's the correct behavior for a stress-energy tensor in dimension d, where d is not an integer. If we're looking at integer dimensions, this has a logarithmic correction, which puts a log there, which is again the expected two-point function of the stress-energy tensor. Okay, so this is, in a sense, the computation of the two-point function of the stress-energy tensor from the late 90s. And now we want to apply this AdS Ricci-flat map to see what happens to that computation. So now we apply AdS Ricci-flat. So then again we get a linearized perturbation, again with the same polarization, transverse places polarization tensor, but now with a new scalar field, which I'm going to call phi naught. So this actually maybe I should call it phi tilde, and let me put a hat here to be similar notation as earlier. So this phi hat, this phi tilde is related to phi hat via the same relation I discussed earlier. So phi tilde is, so we have to put instead of d minus n, so this becomes 1 over k r to the n over 2, k to minus n over 2, which is the same thing as kr to the n over 2, k to n over 2. And that guy here is a solution of the massless equation in a flat background. So that solution, so phi naught, there are two possible solutions. One is specified with the I Bessel function and another with the k. The property of the k that distinguishes the two is that this follows off at infinity. So this is the normalizable mode. So here, the two-point function of the CFT just became, let's say, the standard normalizable mode and it's perfectly flat. So this map is completely canonical. So you get
Circular r equals 0.
the solution I don't remember right now what it's regular.
Is that the very often.
It is the one, yeah. So this falls off at infinity. So maybe by the time I do the next slide, maybe Zwan is gonna.
I'm not sure how to do it, but I think
It's regular at the origin and falling off at infinity, but it will have to be 0.
I mean, the origin, in the sense, it has this correlated behavior, right, at the origin. That's what distinguishes from the other case. Yeah, I was planning to describe what happens to the symmetries when you push it through the map, because, of course, one of the things that the correspondence tell us is that on the Ricci-flat side, there's some hidden conformal invariance, and one would like to flesh it out, and we have started doing this. But if I do that, I'm not going to have any time for black holes, so I'm going to skip that and then discuss a little bit what happens if we try to apply that to black holes. So there we discuss what happens if we apply that, let's say, to the vacuum state of the solution corresponding to the vacuum state of the CFT, or if we do, if we look at excitations around the vacuum. The second case, which is of great interest in holography, is if we start from the thermal state, which corresponds to the black hole. So one would like also to understand whether that state has a useful map. So here, in order to be able to use this map, we need to have this flat torus. So we can. So that's why we start from a planar AdS black hole. So this has this is given by this well-known expression, and then you can just put it into these formulas. And now I'm going to spare you the details. And then when you get on the other end, this is what you get. We're now f of r is 1 minus b over r to the n. And this is nothing but just the Schwarzschild p-brane. And one can also do something else, see what happens if we do not have that sphere. Again, we look at the case of put n plus 1 equals 0. So there's no sphere. And then in that case, what one gets is just after a further change of coordinates, it just gives Rindler. So what I'm going to do in this blackboard, I'm going to kind of finish up with this, is try to see what type of physics we can run from here. And then just using this map, we can see just with few formulas, we get most of the physics that governs that system. So we started on the AdS side. We had a conformal fluid. And the fact that we had a conformal fluid means that the equation of state is given by this expression. Now, if we apply the map, this becomes this expression. So now, if n plus 1 is equal to 0, we see that E is 0 and P is non-zero. That's exactly the properties of so-called Rindler fluid. And if n plus 1 is different than 0, then we can compute the speed of sound and find that this is 1 over this, repeat here. So this is imaginary, and this is nothing but the Gregory-Laflamme instability. So the fact that this system has the Gregory-Laflamme instability is linked to the fact that it is related to a conformal fluid via this correspondence. And one can do a lot more starting from this point, and we do this in the papers. You can start looking at perturbations around it. Like you can do the hydrodynamic regime on the side. When you push it through the map, tells you how the Gregory-Laflamme instability evolves. And then you can also linearize the description and get the dispersion relation of the Gregory-Laflamme modes. And this matches beautifully with numerical data that Paolo did a few years ago. Or you can do this for the Rindler fluid, and this matches exactly the results that we had a few years ago while we analyzed the hydrodynamic regime of the Rindler fluid. So that's a very successful story. So to finish up, in a sense, we're starting uncovering the holographic nature of asymptotically flat spacetimes. There's still a lot of work to be done. because essentially what we did so far, maybe most of the work that we did so far, we set to 0 the sources on the AdS side, except perturbatively, except in this computation I described over here. So to really have an analog of correlation functions on the Ricci-flat side, we have to be able to carry through the entire information encoded on the AdS side, and for that we need to have general sources, and that's something that we're looking at. And of course one can expand on any of these topics, and this is also things we're still exploring, trying to understand the implications of the symmetries, try to see quantitatively what happens to the Gregory-Laflamme instability at the nonlinear level, and all kinds of other fun applications. So, so I hope I convince you that this is an interesting direction. And please join us. Thank you.
If you start with a particular an AdS solution in a particular dimension, is there a unique way to map that onto a Ricci-flat solution? In other words, if you haven't specified it as an arbitrary dimension.
So if you don't know the metric functions as a function of D, we don't know how to go to the other side. So you need a family of solutions parameterized by a dimension. I do think that if one has family of solutions parameterized perhaps by some other parameter, not necessarily the dimension, one will still be able to set up a similar thing. But this is still, I mean, in a sense, this generalized dimensional reduction would still work with other parameters.
Do you think it's possible that you have a particular solution that belongs to more than one arbitrary dimension family of solutions?
I mean, we're still continuing in a orthogonal direction, so to speak. If it belongs to two different families, in a sense, it would turn on different type of moduli, so to speak. It would go to different dimensions. So they would both be interesting to, it would describe different properties of the underlying solution.
Yeah, it's so very simple. Learn that in AdS that it's epoxy additive. And you can make, for instance, a hairy black holes. Right? And you have the Hitler flat thing, it's asymptotically flat. There's no hercium. How to glue them together? How does it work?
So the hair that people usually find are if you have a more complicated system, and then you have, let's say, an IR region that has instabilities. So, I mean, first of all, instability in this map, stable does not automatically map to stable. Like here, the hydrodynamic regime of AdS black holes is clearly stable. And after the map, this maps to the Gregory-Laflamme instability. So the hair on the AdS side that corresponds to IR instabilities would map to some feature on the Minkowski side. What feature this would be? That I don't know. Yeah. But I mean, it's clearly that this is a clearly interesting question, because all peculiarities of one side, they have to manifest one way or another on the other side, and that's the power of if you have such correspondences, that things which are obvious on one side become, say, profound on the other, or completely unintuitive.
Other questions like
Can I ask? It's not clear. It could be that you do get kind of hair in flat, but scalar fields that do become singular at the horizon, for instance. It's not against no hair.
Yeah, you say that the perturbation becomes singular. I mean, so far we have not seen, let's say, a regular map to singular in all the examples we looked. But we don't have a no singularity theorem in this context.
First guess to Europe.
Is that not what's happening in this linear example you give here, that it's something that's normalizable in infinity at AdS has been mapped to something that's singular at the origin in Minkowski?
Is it a check?
It's similar at the origin because of that formula that you have written in that board over there, in which you expand the solution in the AdS side and you look at the asymptotics. The r to the d becomes r to the minus n.
Yes. Yeah. Okay. So yeah.
That confirms my.
What I would say is that what happens there is that the linear approximation breaks down.
Yes.
And nonlinear effects will fix that up.
No, but they can't because the linear approximation is good on the AdS side.
Yeah, on the AdS side, this is everywhere. Yes, regular. So yeah, so that's something to be understood.
So the norm correspondence about storing into the common field to classical graphically, and I would say is classical graphically to classical graphically. So I should understand this operationally that you want to understand what sorting couple of common field theory means in Minkowski, and you use AdS as sort of an intermediate step to translate the field theory through AdS to Minkowski.
Yeah, so in a sense, it's a reality, right? We have, let's say, AdS, which is linked to CFD, and now I give you here Ricci-flat, and okay, my real interest is to find such a relation, and I want to see whether that diagram can help. So far, I have a correspondence here that seems to be sort of canonical, and using that correspondence, I want to kind of push this here. Yes.
Questions that we can make a direct line.
Yes.
So
Yeah, I want to know, what is this? Yeah.
There are more questions.
Yeah, somebody's asking the particulars of this Greger-Laflamme story. I'm still trying to understand funny cases. Like, it's very interesting the way your example here works out. That, for example, if I set n equals 0, where I don't expect to have a black string, I just get flat space, and that's lovely. But do you know what happens with your Greger-Laflamme story if you have this something which is an analytic function of n, and now I set in this context n equals 0, so there's no longer a black brain there. Is
n equals 0 is just going to be
it's flat space.
Yeah.
Yeah.
The rule of the instability, it's the speed of sound is imaginary. So you have an instability where your homogeneity will get distorted, right? Because that's what the sound wave basically are. So if you have a sound mode, and that sound mode, as it propagates, its amplitude increases. So instead of having a homogeneous ground state, you have an instability where there will be clumping.
Right. So I'm trying to understand if I continue that to this context where it's just perturbations of flat space, does it give me something just trivial? Does the instability move on?
But let me also give you one more piece of data. So when you do this, when you start from the hydrodynamic description here, you move it over there. So in order to get that this converges nicely, then you need to take sort of small n, large n limit. Otherwise, this does not give a good description. So the description seems to be that it's more like an asymptotic expansion of the full function, which does not converge well for small n. So when you're in n equals 0, you're really in the region that this description is not very useful.
I see. You say if I look at where the hydro description is useful on the AdS side, it's equivalent to a large dimension limit on
Yes.
the other side.
Yes.
Well, I mean, n equals 0, it's t equals 0, right? So that's function f is 1, so it's really AdS, there's no temperature.
Yeah, I see.
So
I see.
So there's no hydro.
I see.
Yeah, that's
I see. So
that's better. Yes.
you were using
yes.
the hydro approximation on the AdS side. It was not an exact calculation.
Yes. Yes. I mean, of course, the same is true on the AdS side, right? It's the hydro approximation is meant to be asymptotic.
Sure, sure.
And Now, when you map it across, you can see that you need a large small n limit for this to work well. There's a scaling limit that you can take.
Do you have any idea what kind of behavior you need in general on your ADS solution, or your family of ADS solutions, to get asymptotically flat solutions on the Ricci-flat side?
So in this case, in this linearized problem, you see that in order to have a fall-off condition, which would be, let's say, the analog of asymptotically flat, you need to have the standard Dirichlet problem in AdS that in a sense computes the correlation functions. So I think that would persist through all orders. At this point, we only turn on a source only in this specific case. So the standard, let's say, Dirichlet problem in AdS would map to a asymptotically flat problem on the other side. But then you have boundary conditions at the center of the space. Yeah, that's the unconventional.
Okay, I guess you've used the time. Let's thank Kostas again.